We are doing the presentation on DC motors and drives, a study on topologies and troubleshooting. I am Nathan, and he is Vinicius. So this is our routine. We are going to be talking about the basics of direct current motors, pulse-width modulation, H-bridge configuration, half-bridge drivers, a general purpose, BTN 7970, a special case, DRV 8871, an interesting approach, and printed circuit boards layout considerations.
Okay, the first topic of our presentation is the basics of direct current motors. So the first thing we are going to see here is the basic functionality of a DC motor. We use the left-hand rule to see where is the direction of the current, magnetic field, and the force. So here we have the south and the north pole. So we can use the magnetic field to see the current, and we can see that the force will appear here to up and here to down. So with this logic we can establish a rotation in the motor. So the first point of the rotation is in this angle, alpha equal to 0. So the equation for torque is the BIL. So this is the high starting torque that will help to establish the rotation of the motor. When it starts to moving, it will get down the torque of the motor, and in this point will become 0. But the rotation will make sure that this keep moving until appears another torque. The logic behind this is the momentum of the movement that is already in here. So it's basically this way that DC motor will work. In this movement, the force will make sure that the rotation and the inertia will help you to do the rest of the movement.
And we were talking about how motors work, but we have to think about how to control the motor's velocity, the torque, or the acceleration. And we do this using PWM, the pulse-width modulation. So what is PWM, as we say it? PWM is a technique for modulating the DC level of a voltage across a motor or a load in the general sense. So this is how it works. We have a frequency, we are switching on and off the VCC, our highest voltage in the circuit, and so we are establishing an average voltage level. This average voltage level will be the level read by the motor, so that we can control its velocity, torque, and acceleration. So these are the formulae used to do the calculations for the motor's current peak and the average current on the motor, for example. And we establish on our calculations using PWM and such techniques the duty cycle, which is the time in which the power is switched on, divided by the total period of your PWM. So you can set, for example, with a 50% PWM, you can set the half of the motor's peak power, for example. And we can establish an PPWM through a comparator circuit using a triangular waveform and a DC waveform, so that when the triangular wave exceeds the value of the DC wave, you will saturate your wave in the comparator, and you will be setting the PWM levels, the rate, the duty cycle of your PWM.
So here we will see now the H-bridge configuration. This is the basic architecture that we normally use. So if you want to rotate this motor to one side, you basically close these and these MOSFETs, and the current will flow like this. And to the other side, you will close this one and this, so the current can flow like this. The first thing you want to do is close key 1 and key 4, so you create a polarity here, so the current can flow to this center. So will flow from here to here. This and this one, it's open. So the first thing we can see here is a problem that the current can go back to the battery from the reverse way. So this is the normal drive current. So when it's all closed, the current passes from the diodes existing here and go back to the battery from the opposite way. This can cause a lot of trouble and can really damage your battery. So you have to dissipate this power. So to do so, in the brake of the motor, we make a path for the current. You can make here or here. You can also just don't do nothing, but this will certainly damage your battery. This is caused by the inductance of the motor. So he will actually charge, and when you turn off, we will still have some charge here. So you really need to do this to dissipate the current. This is the other way that the current will flow, and you have the same architecture to discharge this current. So it's really easy to do this logic, but you have to take care to never let this and this commutate in the same time, because you can really cause some problems with this. So this is all that we have seen until now. You have this way of current moving the motor like this, and this way of current moving the motor like this. So when you want to stop or change direction, you always need to do this until the charge is over. This can take microseconds or milliseconds sometimes. We'll basically do this and this. This is a more efficient way to architecture your H-bridge. So because that way that we have seen sometimes is very slow. So basically the idea here is that you will use a resistance to discharge faster the current that you have in your inductance here. So to operate this equal to the another one, you can make this just activating Q1 and Q4. But now to discharge, you have to pass your current from here to here, right? Notice that the resistor is always in the way of the current. So you can also make the same thing in the upside of your circuit. You normally choose the one that you will have to change less in your previous circuit. So if you have this direction, you normally choose this one because this is already commutating, so you just have to change one of them, right? You have to turn this off and you have to turn this on. So this way you can really break the rotation of your motor. And you can change the resistance to change also the time of the braking.
And this resistance, it has to be a power resistance, so that it dissipates the charge in the motor properly. So it will dissipate through heat. This will be taken into consideration afterwards.
So this is the other way that we can operate the motor. And you can brake in the same way, but the currents will always be in the opposite. So here is all the options that you have for each type of action that you have here. So okay, now you have seen the drivers that you can activate these H-bridges. If you do this, your current is going from the positive of your battery directly to the ground. This is very dangerous to your battery. You can't do this. So this is actually forbidden. This is the motive that we have to use drivers to activate this circuit. So this is one of them. In that, in this option, one will activate the upside of the MOSFET, and this one it's denied. So you will activate the other one with the 0. So with one here and one here, you have a permitted senses. So this is one of your logics. If you do this, you have the denied one. You can't actually do this. So this driver you have to take care with the logic, but you can do whatever you want with the logic also. So this is when you do nothing or you want to brake, and this is the other way that the motor will rotate. So this is another driver. This is safer because we don't have the non-permitted circuit. Because this, now you will always that if this is turned on, this will be turned off. This guarantees that the current will never flow like this. So to turn this on, you put the 1 here in. So you can set the way that you want. But we have this pin that disable the circuit. So if this is turned with the 1, you will disable the circuit. With the 0, you will enable. So 1 here, 1 and 0. This is on, this is off. 0 here, this is off and this is on. You always have one of the permitted sequences. So you usually will use these 2 hairs that can be very versatile.
Yeah. And now we can be talking about special cases. For example, the BTN 7970 integrated circuit. The BTN7970 integrated circuit is a half-bridge circuit with the MOSFET activators inside it. So inside this chip, you have both the MOSFETs and the half-bridge drivers. So, and he also can hold up to 40 amps of current. So it has a high power compared to its size. We use this BTN7970 in our robotics team here in Federal, the Yapira group. We use it in our bit-08 drivers. The bit-08 motors are usually consuming currents in the houses of approximately 5 amps of current. So with 40 amps in our MOSFETs, we have a pretty good insurance. The only problem with this circuit is that it's a P channel on the high side and a N channel on the low side. So the turn on and turn off times of those MOSFETs is really slow, like half a microsecond. And this generates lots of power peaks, which are not safe for the MOSFETs of the BTN7970. So it tends to be not as reliable as that other configuration with the actual discrete MOSFETs and its drivers. But it's an integrated solution, so it's easier to do layouts with it. Yeah. And this is the internal block diagram of the BTN7970. You can see we have overcurrent detections for both the low side and the high side. We have a overvoltage detection as well. We have overtemperature detection because when you're dealing with high power applications, you have to think about the heat, because the heat will damage your semiconductors. And this is its pin out. We have a ground pin, we have a input pin. This input pin, you can actually choose which side of the half-edge bridge is being activated. The inhibit is the pin to which we use the PWM, so it won't get as hot as you could get with PWMing the input. And the slew rate, you can choose the slew rate of the integrated circuit. This is an application circuit using the BTN7970. This is a layout done with it. This is a board that can hold up to 40 amps of current, the limit of the BTN7970. And it's like 70 millimeters in one side and 40 millimeters in the other side. So it's really small compared to the current it can hold up. And we can be talking as well about low power applications with DRV8871, which is a full bridge circuit. And it's really small. The University of São Paulo robotics team made a driver with this IC, and their driver had like 20 millimeters of width and 24 millimeters of length. So it's really small. And this IC can hold up to 3.6 amps of current. So compared to its size, to its small size, it really handles well such power. And it's used, the DRV8871 use is really simplified. So for engineers, it's a really great feature to have. This is a topology using the DRV8871. As you can see, it's not complicated at all. Just some capacitors here to eliminate noise. The motor, it even has ground separation and a limitation of current inside the DRV8871. And this is the driver that University of São Paulo made. As you can see, it's a double-phased one, and it's really small with a high current. It's really efficient. And now, lastly, we'll be talking about the printed circuit board layout considerations. Usually, when dealing with high-power applications, we have to make straightforward and short connections in our circuit. Because, you see, 1 millimeter of PCB length gives us an inductance of 1 nanohenry. So this is not really desirable and can and will be destructive to our motor. We don't really want any inductance on the circuit. So when we make straightforward and short connections, we are reducing that inductance.
It's very important to you to create power planes to dissipate the current that you will have in the motor because of the inductance of them. So you create normally one to VCC, one to the ground, and one to the microcontroller ground. So the fluctuation of the power this way will affect less than if you don't create nothing, because that fluctuation can actually turn off your microcontroller and will just stop working the system that you have created.
And you have to make thicker routes in your PCB because you see the current is really big and you have to handle it. But with short and straightforward connections, as I said, you don't have a lot of dissipation to make in the route, so you have to make it thicker and not bigger. You also have to think about heat sinking, as I've said, because semiconductor components usually don't cope well with heat. You also have to make troubleshooting vias, which are holes in your board made to troubleshoot it. You can test each one of the pins in your integrated circuit and see how your control feedback is dealing with all sorts of problems in the circuit. And as you said, there is a problem with motor noise, and to deal with it, we use ground isolation. So we isolate the power plane, the power ground, and the control ground, so that the noise from the motor won't go to the microcontroller to the ground. And I think that's it. Thank you very much.